so-called X state, right? So the chemical physicists are not very imaginative people. They just call the ground ionic state. Ground ionic state is always called the X state, and then the first excited ionic state, right? This one, because that one's slightly higher in energy, is called the A state, and then the next one up is B, C, D, E, F, and so forth. So only the ground one you call it X, ground ionic state, ground call it X, and then you label alphabetically for all the excited ionic state A, B, C, and so forth. Okay, so that's a notation that you got. Now, what happened in photoelectron spectroscopy? Well, if you take your photon energy, I represent the photon energy. Let's say you have a photon which you generate by exciting helium atom, and then letting the helium atom coming back down from this excited state, right? It emit a little photon because you first excite your helium atom by high voltage, if you like. You put helium atom between two plates, and you basically excite them by high voltage excitation. So the helium atom somehow get to the excited state, and then this excited helium atom go back down to the ground state. And in the process, it emit different amount of photon. And one of the type of photon that emit is 21.2 electron volt. This is called a helium-1 resonant line. Very much like your neon sign, your neon D line that you see in all the neon sign that you see, that's due to excitation as well. So all the different color that you see is due to excitation. In this case, it's not emitting a color, it's emitting in an ultraviolet, so you don't see, it's invisible to a human eye because it's not visible light, but it's ultraviolet light. So it's the same concept that you bring it up to excited state, and the excited state decay back down and emit a photon. So that's called resonant line. And so you take this resonant line and use it to excite your system. In this case, water, right? What would happen? Well, so you have a discrete amount of energy, right? A package of energy, 21.2 eV. And basically what you have is you let the water absorb the entire photon, 21.2 electron volt. So let's say you are right here, right? Let's say the lone pair electron right there, it absorbs, this lone pair electron absorbs the entire 21.2 electron volt. So what does it need to do? It needs to first overcome about 11 electron volt, because this is so-called the binding energy of this electron in this orbital. So you have to first overcome the molecular field, 11 electron volt, to the vacuum level. The zero binding energy corresponds to what we call vacuum level. This is the energy where, this is the energy state when the electron become a free electron. It just overcome this molecular field, and then the rest of the energy it has to carry over. So you have 11 volt taken up by the overcoming the molecular field, and the rest, right? Because it still contains 10 electron volts. So the 10 electron volt of these free electron will be moving with a kinetic energy of 10 electron volt. So so this kinetic energy plus this, right, correspond to the entire photon energy, which is 21.2 electron volt. Okay, so this is what the Einstein equation is talking about. So you have a fixed photon, 21.2 electron volt. This is the binding energy, the energy required to overcome the molecular field for that electron, and then the rest of this energy will exhibit as kinetic energy of that electron. After it overcome the molecular field, it becomes a free electron, and the excess will be carried out as kinetic energy. Okay, so if you do that, you get one peak. You can see this peak right here. Okay, and in your photoelectron spectrum, that's what you see. So you see the ionization energy, which correspond to the binding energy. So this is around 11 electron volt right here, and correspondingly, if you take 21.2 minus 11 electron volt, it corresponds on the upper scale here. It corresponds to kinetic energy, which is this guy here. So that gives you about 10 electron volt for the kinetic energy. Okay, you can see that these two are connected to each other by the photon energy. Okay, and what happened? Okay, so now if you imagine that you are scanning your photon, let's say your lone pair electron absorb the entire photon, but not just the lone pair electron absorb the entire photon. You could have the other electron absorb the photon as well. So let's say you have free A1 orbital absorb the photon, and what happened? Well, you can imagine this is a fixed ruler. You just slide down the ruler a little bit to here, right? This orbital and the electron take up the entire 21.2 eV energy, right, in here, and it will then first overcome this molecular field. It will get excited, so it go to it take about 12.7 electron volt to overcome its own molecular field to the vacuum level, the level when it just becomes free electron, and then the rest of it, about 9 volt or so, left behind, will be taken up by this electron as free energy, right? So it will have less kinetic energy, right? So that corresponds to this state here, this little peak that you see here, this peak here that you got. Okay, so that's called the this is called the X state, the ground ionic state. The A state corresponds to the excited ionic state, and you can see it's higher in binding energy because this orbital lies deeper in the molecular field, and it has correspondingly lower kinetic energy because it needs more energy to overcome this binding energy, and then whatever left behind is carried out as kinetic energy. Okay, so that's the basic idea, and then you can keep going down, right, up to about, let's say, the 1b2 orbital, this 1b2 orbital, and then you run out of energy because by the time you go all of 21.2 eV photon, you don't have enough energy to overcome the molecular field. So, for example, you will not have enough energy to overcome the two-way 1 orbital because it's deep down. It's more, the binding energy is a lot more than 21.2 electron volt. You don't have enough energy to overcome the 1A1 orbital, which is about 550 electron volt. So that UV photon is not sufficient. Okay, so you will not see these guys. You will not see these two, but you will see, probably you will see these three